Okay, so we continue with problem 12 in section 2.3. So we're given two linear transformations, T and U, T from V to W and U from W to Z. We need to prove that if UT is onto, then U is onto, and we have to answer the question, must T also be onto? Okay, so we suppose UT is onto. Okay, and we want to show U is onto. Okay, so remember UT goes from V to Z and U goes from W to Z. Okay, so we'll let Z be any vector in Z. So since UT is onto, there is a vector V in V such that UT of V is equal to Z. But this implies that U of W is equal to Z, where W equals T of V, and this is a vector in W. So here we found a vector W in W such that U of W equals Z, where Z is any given vector in Z, hence U is onto. Okay, so we'll show that this does not necessarily imply that T must be onto, so we need to come up with an example. So this is relatively easy. Okay, so we'll let T go from R to R2 by T of a number X is the vector X0. So this is clearly a transformation because X0 is equal to 10 times X. T is linear, and clearly T is not onto, since the range of T is the set of vectors that look like X0 such that X is in R, and that is definitely not equal to R2. Okay, so we need to come up with a transformation U such that UT is onto. So what we do is we let U go from R2 to R by U of a vector xy is the number X, which is linear because this is equal to xy times the matrix 1, 0 on the left And if we look at UT, okay, so UT goes from R to R. UT of x equals U of x0. That's equal to x. So that means that UT is the identity in R, which is onto. So even though UT is onto, that does not mean that T is onto, because in this example, this T is not onto, but UT is onto.